In the previous video, we talked about our first energy storage device, the capacitor. A capacitor is a device consisting of two conductors separated by an insulator. A capacitor stores electrical energy in an electric field that exists between the positive charges on one of the conductors and the negative charges on the other conductor. Now, energy in the form of an electric field is a little bit mystical, in the same sort of way that gravity is a little bit mystical. However, we can imagine it and sort of even think our way through it. There's an invisible attractive force between two objects. This can be the attractive force between two bodies that have a mass, as in gravity. It could be the attractive force that is between charges that have an opposite polarity. It could even be the invisible attractive force between the north and south poles of a permanent magnet. It simply causes two objects to be drawn toward each other. Or if they happen to be like charges or magnetic poles, pushed away from each other. Where things really start to get strange to me is when electric and magnetic phenomena interact. Once we enter the realm of James Clerk Maxwell, the world becomes strange enough that explanations involving elves to deal with vector quantities and hobbits to deal with everything else mysterious seem quite reasonable. This is the realm that we enter when we start talking about inductors. The simplest form of an inductor is a loop of wire. When we pass current through a loop of wire, the circular motion of the current through the loop produces a magnetic field perpendicular to the plane of the current. Like most things, we cannot necessarily explain why this is the case, but we do know that it is a case. For engineers, that's usually good enough. An element of mystery is okay. We don't need to comprehensively understand something in order to use it for our benefit. Actually, if the relationship between electric current and magnetic fields makes complete sense to you, I would guess you've lost your sense of wonder when looking at the universe. And if it makes no sense to you, give it time. Some of the pieces will eventually fall into place. Rather than delving too deep into electromagnetism or philosophy, let's take the relationship between electric current and magnetic fields as a given. Electric current traveling in a loop produces a magnetic field. The magnetic field will be perpendicular to the plane of the current in the direction given by the right-hand rule. So, if the current is traveling in the direction the fingers on your right hand curl, the magnetic field will be in the direction of your thumb. This magnetic field is where the energy is stored in the inductor. A magnetic field may not intuitively seem like energy to us, but if we remember that the definition of energy is the ability to do work, it should become apparent. If you ever happen to watch an old police-type television show from the 1970s, at some point you likely saw a scene at a junkyard where some helpless victim or the hero of the show was trapped in a car that was being put into a metal compactor. As usual, with overly dramatic methods like this, the victim was always rescued, or the hero narrowly escaped at the last second. Often this car was picked up and put into the compactor by an electromagnet. An electromagnet is simply an inductor with a ferromagnetic material in the center. When current passes through the inductor, the magnet is turned on and becomes a powerful magnet. And when the current stops, the magnet drops whatever it had picked up. The point is, picking up cars is definitely work, so there must be real energy there. In fact, magnetic flux can be expressed as energy over current. The inductance of a loop is the ratio of the magnetic flux to the current responsible for the flux. The unit of inductance is the Henry, named in honor of Joseph Henry, where 1 Henry is 1 Weber over 1 ampere. Like the basic unit of capacitance, the basic unit of inductance represents a very large inductance. To make a single wire inductor, a single loop of 3/0 wire would have to be over 1,000 feet or 320 meters in diameter to result in 1 Henry of inductance. Typical inductor values range from nanohenries to millihenries. They are generally constructed by tightly coiling wire, sometimes with a ferrite or magnetic material inside the coil. The inductance of the coil of wire is given by this equation. Mu naught is called the permeability of free space, equal to 4 pi times 10 to the negative 7th henries per meter, or newtons per amp squared. Permeability is related to how easily a magnetic field can be formed in the medium. Materials such as iron have a much higher permeability than space. N is the number of loops in the wire, and A is the cross-sectional area of the loop, and L is the length of the coil. Like with the capacitor, the current voltage relationship for an inductor is differential. However, the voltage is proportional to the derivative of the current with respect to time. This means that if the current through the loop is constant, the voltage across the inductor will be 0. This should make sense to us since the inductor is a wire, so when everything is in equilibrium, it should look like a wire. We can also see that if the current changes quickly, with the extreme being illustrated by the time interval going to 0, the derivative of the current with respect to time becomes infinite. Infinite voltage would likely have made Tesla happy, but cannot exist. An infinite electric potential would arc through the entire universe. In basic terms, we can say that an inductor looks like a short circuit to DC, and inductors do not allow instantaneous current changes. The latter of these leads to some of the most basic uses for inductors: resisting current spikes, as in rudimentary surge protection, or generating large electric potentials by producing current spikes through the inductor, as in switching power supplies. Brandon, can we talk about inductors once without you getting hopelessly tangled up in wire? I'll send somebody for the wire cutters. Given the current voltage relationship for the inductor, in which we see that the voltage is the inductance times the derivative of the current with respect to time, we can perform some simple algebraic manipulations and rearrange the equation to express the time-dependent current through the inductor. With some thread of calculus, we see that the current is determined by the integral of the voltage. Now, since we know the current voltage relationship for the inductor and we know the equation for power, we should be able to derive an equation for the energy stored in an inductor. Starting with power equals voltage times current, using the inductor current and the inductor voltage being equal to the inductance times the derivative of the current, we can write the power equation for an inductor like this. Applying dt to both sides, we can then integrate the power on the left side with respect to time and the current on the right side with respect to current. From this, we get the difference in energy between the time we're interested in and the initial time is equal to 1/2 times the inductance times the difference of the currents squared. That is not only difficult to say, it's difficult to look at. So we usually write the energy stored as 1/2 times the inductance times the square of the inductor current. Since it is the electric current that produces the magnetic field that stores the energy in an inductor, we should not be surprised that the energy stored is related to the current through the inductor. One thing that is different about the energy storage in an inductor as compared to the capacitor is that the source must be present for the inductor to store energy. The energy storage of the capacitor is based on charge and could therefore still exist under static conditions. The energy storage of the inductor is based on current, since current is the movement of charge, and this is a dynamic event. Once the current stops, there is no longer any magnetic field and therefore no more energy storage. Let's calculate the energy stored in an inductor in a particular circuit. If we connect a 5 millihenry inductor to a 0.5 amp source, we can substitute those values into the energy equation, and from that determine that the energy stored is 625 microjoules. That may not sound like a lot of energy, but it is about the kinetic energy of more than 1,000 mosquitoes flying at you, assuming a flight speed of 1.5 miles per hour and a mass of about 2.5 micrograms per mosquito. If we put an inductor in a circuit with a couple of resistors and assume the circuit has been like this for a while, about 5 milliseconds or so, we can determine the current through the inductor by determining the current through the 2 ohm resistor. This is because an inductor looks like a short circuit to direct current. We can then use current division to solve for the current and find that it is 0.3 amps. The energy stored in the inductor would then be 1/2 times 5 millihenries times 0.3 amps squared, or 225 microjoules. Before we call it a day, we should take a look at series and parallel inductors. We can use Kirchhoff's law to see the effect of connecting two inductors in series. If we write a voltage loop around this path, we can substitute the current voltage relationship for the inductor. Since the inductors are in series, the current through them will be the same. We can then factor out the derivative of the current, which gives us the voltage is equal to the sum of the inductors times the derivative of the current. The sum of the inductors is the equivalent of the inductors in series. So to combine series inductors, we simply add their values. This is true no matter how many inductors are in series. If we have two inductors in parallel, we can write a Kirchhoff's current law equation at the top node and then substitute the voltage integral. Since the inductors are in parallel, the voltage across them are equal. We can then factor out the integral of the voltage so that we are left with the sum of the reciprocals of the inductances, which is 1 over the equivalent inductance. So parallel inductors add reciprocally. This is true no matter how many inductors are in parallel. I'll let you verify that on your own if you're interested. A quick review. Inductance is a ratio of magnetic flux to current and is measured in henries. From the physical construction and the differential current voltage relationship, we determined that the inductor is a short to DC signals. We also saw that if you tried to change the current through an inductor instantaneously, the voltage would become infinite. Since this can't happen, current through the inductor cannot change instantaneously. We determined how to calculate the energy stored in an inductor and that the energy was related to the current through the inductor. We then looked at how we might solve a simple DC circuit involving an inductor. Finally, we figured out how to combine series and parallel inductors. Inductors are a class of components that sneak into our lives all over the place, and we could spend a lot of time discussing them. Maybe some other time. For now, that's all for today. Go out and make it a great one.